Good day, viewers all over the world. Welcome to Today online class. So I want to discuss set theory. So the topic is set theory. So what is set? A set is a collection of well-defined objects or items. Is a collection of well-defined objects or items. For instance, if we talk about a set of a nuclear family, let's denote the set as maybe F. That set comprises the father, the mother, and the children. So, if you talk about the set of a nuclear family, of course, a nuclear family is a family where you have father, mother, and the children, depending on the nature of the family. So, in this case now, this set F is clearly defined. So, the word well defined must be specified whenever you are discussing about a set. So, we denote a set by capital letters. We denote a set by capital letters, an element of the set by small letters. Element of the set by small letters. That's what we do. So whenever you want to denote a set, you use a capital letter, and the element of that set, you denote it by small letters. Not only that, we use curly brackets to represent a set. It's different from ordinary brackets. So it is curly bracket that we use whenever we want to represent a set. So all this must be clearly stated if you want to give a definition or you want to represent a particular information in terms of a set theory. So a set is the collection of well-defined items or objects. So it is completely specified in the following ways, either by listing all the elements like set A is equal to A, B, C, or by describing the elements of the set. In this case now, I can say A belongs to the set of A. So we can do that, or by enclosing with braces, like what we have there. We can also represent sets in form of a diagram, and that one is what we call the Venn diagram. So that's that about sets. Then I'm going to talk about some definitions. That is, when we talk about definitions, we can talk about the element of the set. Elements, elements of a set. So elements of a set are members of a set, and are often called the members of a set are often called the element of a set. For instance, under the set of, or I've introduced the set of numbers. When we have a natural numbers, these are positive counting numbers. Okay, so natural numbers in that set we have 1, 2, 3, 1,000,000, 1,000,000,000, 1,000,000,000,000. So, but in the set, if you want to truncate the element of a set, after that comma, just put 3 dots. It simply means that, and so on. So this is the element in the set of natural numbers. That is the positive counting numbers. If you have integers, the set there starts from minus infinity, dot dot dot. We say -1 is 0, 1, dot 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 to positive infinity. That is, this set now comprises positive whole numbers, 0, and negative whole numbers. You understand? So this is how to represent the element of a set. Then there's what we call equality of sets. So when we have two sets, say set A and B, these two sets are said to be equal if the element of A, element that you have in set A, is the same element that you have in set B, irrespective of the arrangement and if there's repetition. But as long as the element you have in A, you also have it in B, then we can say set A is equal to set B. That is that about equality of sets. That is, then we can talk about another concept which is called empty sets. That is, empty set is the set. Empty set, number 3, empty set. Empty set is the set that has no elements. That is, if you have a set that has no elements, and this is the notation This is notation for empty set, or or you represent it as phi. So empty set is the set that has no elements. Is the set that has no elements, as we have it on the board. For instance, let's say set of human being with four heads. In the natural sense, we cannot get it, but I wouldn't know. In the abnormal sense, it's possible. But we go after reality here. So empty set is a set without elements. Then there's another one that we call unit sets or singleton sets or unit sets. This is a set that has just one element. If a set has only one element, for instance, when you have something like this, there is difference between this and this. In case of empty sets, you denote it as this or phi. But in case of singleton set or unit set, it has one element, zero, or you can call it O. So this is different from this. They are not the same set. Empty set, no element. Singleton set, just one element. Then we can talk about another concept called the finite. I'm trying to define this just under definition of terms. These are some of the concepts that we are going to use when we want to solve problems under set theory. We have finite or infinite sets. So what is the difference between finite and infinite sets? Finite set is a set that has a specific number of elements. That is, let's say set A is equal to the letters that we have in the alphabet A, B, C, up to Z. Of course, we know that there are 26 alphabets in English language. So this is specific. So finite set is a set that has a specific number of elements. But infinite set is a set that does not have a specific number of elements. For instance, set of natural numbers. It starts from 1, 2, 3, dot, dot, dot. So in this case now, we cannot find the cardinality here. Cardinality simply means the number of elements in a set. In a finite set, we can find the cardinality. But in an infinite set, we cannot find the cardinality. That is, we cannot know the actual number of elements in that set. And that set is called infinite set. But in a situation whereby we can know the specific number of elements in a set, then that set is called finite set. Then we can talk about cardinality of a set. Cardinality. Cardinality of a set. This is just the number of elements that we have in a set. So the number of elements that we have in a set, we can denote, for instance, this set A now. The cardinality of A will be 26 because there are 26 alphabet letters in English language from A to Z. So that is that about cardinality. Cardinality of a set is just the number of elements that we have in that set. Then another thing that we can talk about is universal set. Universal set. I'm still on that definition of terms. Universal. Universal set. So in case of universal set is the largest set under consideration. That is, any set that we want to discuss, the largest set under consideration is the universal set. So it is the largest set under consideration. And it can also be referred to as the mother set. That is the highest set under consideration. That is universal set. Then there's what we call the union of a set. So the union of sets. So it has this notation. The union of a set simply means or or both. For instance, if you have set A and set B, the union of set A and B is represented as this. It simply means that the element that you have in A, or you have that element in B, or you have the element in both. So that's the meaning of union. Union simply means or, or both. That's the simple interpretation of union of a set. Then we also have what is called the intersection. The intersection of a set. Intersection of sets is denoted as just like inverted symbol for union. This intersection simply means and. That is, if you have A intersection B, this simply means that the element that you are going to pick in this set simply means that the element must be in A and it must be in B. So when you have union, the simple interpretation is that interpretation is just or either the element is in A or B or both. But when it comes to intersection, the element must be in A, that is complement of sets. So we talk about complement of a set. For instance, if you have a universal set, say from 1, 2 up to 10, this universal set, and you have a set A, which is even 2, 4, 6, 8, 10, and you have set B, which is 7 and stop. The element that you have in the universal that are not in A, that's the meaning of complement of a set. That is, if I have to find A complement here, A complements are the element that you have inside the universal that you don't have in A. So in this case now, A complement will now be 1, 3, 5, 7, and 9. So these are the elements that you have in the universal that are not in A. So I can also ask you to find B complement. B complement will be 2, 4, 6, 8, 9, 10. B complement will be the element that you have in the universal that are not in B. So that is simple interpretation of complement of a set. Then we can also talk about subsets. That is subset. Also, in this case now, if you want to talk about subset, subset simply means subset is subset. Subset simply means if it's a part of the universal. For instance, A now is a subset. This is symbol for subset. It's a subset of the universal set. That is, all the elements that you have in A are also in the universal. So all the elements here is inside the universal. Then we can have proper subsets. That simply proper subset simply means if the element you have in A is the same element that you have at the universal, so it can be referred to as proper subset. But we should take note that set can be represented by a Venn diagram. We can represent set in a diagrammatic form. That's a simple interpretation. For instance, this set A now, I can decide to represent it in form of a circle. I can just draw a dark circle and say this is A. So how many elements do we have in A? 5. I'll just say 2, 4, 6, 8, 10. So it's either I represent my set in this form by listening, or I can represent it in form of a diagram. So this is called Venn diagram. When we represent set in form of a diagram, it is called Venn diagram. Then there's some other concepts that we need to talk about under set. So as we proceed, we'll make reference to some of the concepts that we have not discussed about. So that's just simple introduction to sets. So let's give example. Let's say example one. Example one. Let's just give example just to buttress our point. Example one. And it says if the universal is given as 1, 2, 3, dot 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 to 30. This is the universal. And M, set M is given as 2, 4, 6, dot 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 20. Okay. Then we have another set N given as 1, 3, 5, dot 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 19. So we have another set S. These are subsets of the universal. So universal is the largest set under consideration, 30. So you realize that all the elements that you have in M, N, and S, they are subsets of the universal. So the question now says, we should find the cardinality of the universal, that is, number of elements at the universal. Roman figure 2, we should find the cardinality of N prime, that is, the complement of N. Then 3, we have to find number of elements in N plus the cardinality in X. Then the last one, we should find the cardinality of M prime, that is complement, plus the cardinality of S complement. So what do we do here? In this case now, the first question, what is the cardinality of the universal? That is, how many elements do we have at the universal from 1 to 30? That will be 30 elements. That's just the first one. Then, what is the cardinality of N prime? What is N prime? N prime is just the element that you have in the universal that are not in N. So for us to be able to find that, we will first list all the elements that we have N prime, we list all the elements in N prime. So when we look at N, there are set of odd numbers from 1 to 19. Then we are going to have 2 there, 4, 6, 8, 10, 12, 14, 16, 18, 20. Then from 20, we continue to list 21, 22, 23, 24, 25, 26, 27, 28, 29, then 30. So how many elements? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 19, 20. So from there now, we can go ahead and find Roman figure 2, the cardinality of n prime. The cardinality of the complement of n, which is n prime, is 20. That is, we can't just get the number of elements without listing it. Then another one is that this Roman figure 3, we have to find the cardinality of element in n. N now, there are 10 elements because 1, 3, 5, 7, 9, if you list it, is 10. Then cardinality of x, that is number of elements in x. S is from 10 to 30, and that will be 21. 10, 11, from 10 to 20, 30 is 21. So if you add the two together, we are going to get 31. So that's what we are going to get. Now look at, we have to find the cardinality of elements in M prime, that is M complement, plus the number of elements in S complement. So how do we get that? How do we get that? So we are going to list it out. So what is M prime? M, we first find M prime. M prime simply means elements here that are not in the universal. We have 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. Of course, 20 is there. Then 21, dot, dot, dot to 30. So there are, in this M prime now, cardinality of elements, the total element in M prime will be 20. Then what else are we looking for? S prime. What is S? S is from 10 to 30. Then S prime will be elements that we have in universal that are not in X. So S prime will now be 1, 2, 3, 4, 5, 6, 7, 8, 9. So cardinality, number of elements in S prime is equal to 9. Then the answer to this given question, the fourth one will now be, what is the total element that we have in M prime? Is 20 plus 9, and that gives 29. So that is just introduction. So that is what you get from the question. So we can take another question. Let's take another example. Let's take another example. We take another example. So example 2. Example 2. In this example now, we have if A is equal to 3, 5, 6, 8, and 9. If A is equal to, and B is equal to 2, 3, 4, 5. So the question now says that we should write down the set A union B and A intersection B. So the question now says further that we should show A and B on a Venn diagram. Solution. So this is A. A is given as this, and this is B. So the first one, what is A union B? A union B will be the element that you have in A or B or both. Then let's check it out. We have 2 in B, we don't have in A, you pick it. We have 3 in both, you pick it. We have 4 in B, not in A, you pick it. You have 5 in both, you pick it. 6, 8, and 9. So this is A union B. The element that you have in A or B or both, that is A union B. Then what is A intersection B? A intersection B simply means the element that you have in A and B. The element that you have in A, and you also have it in B, that is A intersection B. So what are the elements? The element that is common is only 3 and 5. So 3 and 5 is the element that you can have in both. Okay? Then how do we now represent this in Venn diagram? So Venn diagram simply means representative set in form of a diagram. So there are two sets here, A and B, but they have 3 and 5 in common. That simply means that there will be overlap. If this is A, then I can draw B beside this, but it will overlap because they have something in common. So these 3 and 5 that they have in common will be at the intersection. So this intersection, I'm going to treat Venn diagram. We are still going to treat Venn diagram. Then what do we have left in A? A in A now we have in A we have 3, 5. So we have 6, 8, 9 here. Then in B, what do we have left? 2 and 4. That is how we can represent that question in Venn diagram. So in diagrammatic form. So we can also give. Let me also give another example. Let me give another example. Given that the universal is equal to A, B, C, D, E, F, and X is equal to A, B, C, D, Y is equal to C, D, E, and Z is equal to B, D, F. So the question now says the following. List the following. Number one, the first one, X union Y. The second question, we have to list X union Y union Z. Okay. So another one, we have to list X union Y intersection Z. Then another one, we have to list X intersection Z. Then the final one, so we have to list X intersection Y union X intersection Z. That is all that we are required to do. So after this, I will introduce set builder notations, then I will stop the class. The first one now, we have X union Y. What is X union Y? Element that you have in X or Y or both. So in this case now, we have A in X, we have B, we have C, we have D, and E. That is X union Y. Then the second one, we have X union, we first find Y union Z. What is Y union Z? Consider Y and Z. So in Y, we have CDE. In Z, we have BDF. So Y union Z will be B. B is there. C, D, E, F. That's what we are going to get. But the question says X union into Y union Z. So now let's compare the element of Y union Z and X. So in Y union Z, we have from B to F. But in X, we have from A to C. So that will now be A, B, C, D, E, F. And this is same thing as the universal. That is what we are going to get. Then the next one, we want to find number 3. We want to find X union Y. We have gotten that. X union Y is what we have here. Then intersection Z. What is Z? This is Z. So X union Y intersection Z will now be X union Y is number 1. Then let's compare X union Y, that first solution, plus Z. What do they have in common? B is common and D is common. They already have B, D as the intersection. Okay. Then what is X intersection D? X intersection Z. X and Z, what do they have in common? It's only B, D. So X intersection Z is BD. Then the fourth one, we have X intersection Z. They have BD as something that is common. X intersection Z. No, X intersection Z have BD. Okay. Then the last one, the last question is where we have the last question is where we have X intersection Y. X intersection Y is given us. Let's first find that one. X intersection Y, X and Y, what do they have in common? That is CD. CD. Then what is X intersection Z? Of course, we know that one as X intersection Z is BD. So X intersection Y, then union X intersection Z will now be, compare these two, it will be BCD. And that is what we are expected to do. Okay, that is what we are expected to do. So I will just introduce set bidder notations. I will introduce set bidder notations. Then we continue from there in our next class. So set bidder notations, set builders, set bidder notation, set bidder notation. So how do we set set of values can be represented in set builders notation. So for instance, if we have A to be equal to dot minus 2 minus 1 0 1 2 3. If you have A to be equal to what you have on the board. So how can we represent this in form of set builder notations? That is, look at A. It's a set of integers because it comprises the positive whole numbers 0 and negative whole numbers from minus infinity. So how can we represent this? So this can be rewritten. It can be written as A being equal to, so let's represent each of these elements as X. We represent each of these elements as X, such that the column here is called, this column is called such that, okay, the column is called such that X is less than 4. That is, X belongs to set of integers. Please, let's look up very well. This set A now is an infinite set. We don't know the specific number of elements in this set A. The set continues from minus 1 billion, 1 trillion, 1 billion, blah, 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 up to 3. So all the negative whole numbers that you can think of, they are part of this set. Dot, dot, dot simply means this set is from minus infinity. But we truncate the set as 3. Then if I don't want to write the set here, what if you are given something like this? If you are given something like this, can you interpret it as this? That is the question. Because what you normally do under set bidder notation is that you represent each of the elements of this set. Let's represent it as X. We put column such that X is less than 4. Then we must tell us X is a natural number, integers, rational, irrational, real, or complex number. Okay, like I've treated a topic called set of numbers. So you can just revise on set of numbers. That is what you are going to get. Okay, so where X is an integer. So then I can just list about 2 or 3 examples. Then I will list the example in form of set bidder, in form of this set bidder notations. Then I will ask you to express it in this form. That is what I'm about to introduce now. So irrespective of how the question is given, you should be able to interpret it. And that is the idea on this. Let's see example 4. So the question says, list the elements of the following sets. That is A. The first element is where you have S such that 3 is less than X, less than or equal to 5. X belongs to natural numbers. So then B, we have S such that S is greater than or equal to minus 2. X belongs to integers. Then C, we have X such that minus 10 is less than X, less than 5. So X belongs to integer. Then let's say the last one, X such that S is greater than 8. Then X belongs to integers. So how do we rewrite this? That is the idea, what we want to do. The first one now, How do we rewrite the set? Look at it. We are given x such that 3 is less than x, less than or equal to 5. X is a natural number. Then the set of elements that we have there is that if 3 is less than x, it simply means that x is greater than 3. Then if x is less than or equal to 5, it simply means that 5 is greater than or equal to x. So in this case now, the element that we are going to have is that x is greater than 3. If 3 is less than x, x is greater than 3. So the element will start from 4. But x is less than or equal to 5. This is less than or equal to. Had it been what you have here is less than 5, it's only 4 that we have in that set. But since we have equality, we can include 5. And that is the set. What if you are given your set in this form? Can you represent it in set beta notations? That's the question. Then the second one, we have x such that s is greater than minus 2. So if s is greater than or equal to minus 2, then what are the elements that we are going to have in the set? It simply means that minus 2 is less than or equal to x. Okay? So the element will start from minus 2. So we are going to get minus 2 here. Minus 1 is 0, 1, 2, dot, 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 up to infinity. Because this second one is a set of integers. Once there is minus, we are talking about integers. Okay? But if it's positive whole numbers, it's natural number. That is natural number. Then the third one, C, we have x such that minus 10 is less than x less than 5. Then what do we have there? If minus 10 is less than x, it simply means that x is greater than minus 10. Then the number that follow minus 10 is minus 9, minus 8. We are going to list out the number to 4. Dot, 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 3, 4. These are the elements that we are going to have. Okay? Then if I'm given this element, I should be able to write it back in set beta notations. Then the last example here, we have x such that s is greater than 8. S is an integer. So if s is greater than 8, the first element will be 9, 10, 11, dot, 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 up to infinity. So we have been able to rewrite the question from set beta notations to the normal one. So if you are given this, you should be able to represent it in set builders notation. So I would love to stop here. I would love to stop here because of our time. So we are going to continue from here. We'll continue from here. So I'm going to introduce Venn diagram and problem solving in our next class. That is, how do we represent all this information in form of a diagram? And that is what is called the Venn diagram and problem solving. So by the grace of God, we are going to consider that in our next lecture. Thank you for listening.